Welcome to this third lecture on the growth of functions. In this first segment, we're going to start by reviewing some important facts about the growth of reference functions, and then we're going to use these reference functions to establish bigger relationships for arbitrary functions. So first, let's start by discussing the reference functions we already analyzed earlier. So in this table, the leftmost column is a list of reference functions, g of n. So each row corresponds to a separate reference function. Now the rightmost column is simply the common name given to these reference functions. So for example, the function g of n equals to k. Since that function does not depend on n, it's a constant, and so it's called a constant function. As you remember, the function logarithm base 2 of n is called the logarithmic function, and so on and so forth. Now, the most important feature of this table is that the reference functions are listed in a very specific order. In fact, they are listed in the order of their rate of growth, from the smallest rate of growth, or the function that grows the slowest, all the way up to the function that grows the fastest. So let's make sure we indicate this for you to remember that the order of the rows in the table means that if a reference function appears below another reference function, then the first function grows faster than the one above it. And this is true for every single pair of reference function in this table. First, let's review what we already know about reference functions. The logarithmic function is upper bounded by the linear function, which is upper bounded by the linear arithmetic function, which doesn't grow as fast as any of the polynomial functions of degree 2 and larger. All of the polynomial functions are upper bounded by all of the exponential functions, whatever the value of the base k is. So if k is equal to 2, the function 2 to the power n is an upper bound on all of the polynomial functions. Of course, if k is larger than 2, like 3, the function 3 power n grows even faster than 2 power n. Then the factorial function is an upper bound on the exponential functions, and the function n to the power n also grows faster than the factorial function. Now, let's consider a couple new facts maybe. First, let's focus on the constant function. G of n is equal to a constant k. So what does it mean when we say that a function f of n is bigger of a constant? Well, in particular, that means that the value of f of n does not grow when n increases, or at least it does not grow beyond a particular constant. So the constant k could be any real value, like 1, 2, 2.5, 10, or even a negative value. But in general, when we say f of n is bigger of a constant, we always use the constant 1. So why is that? Well, if you were tempted to use a larger value like 10, it doesn't really matter, because if f of n is bigger of a constant, remember that means you can always multiply the function g of n, namely k, by an arbitrary constant c to upper bound the function f of n. So you might as well use the constant function 1, and if you needed a bigger constant, it would just get wrapped up into the constant c of the bigger relationship. So the bottom line is, every time a function is upper bounded by a constant, you always say bigger of 1, as opposed to bigger of 5 or bigger of 10. Now remember that the graph of the constant function is a straight horizontal line. In fact, this function is the only one in the table that is not strictly increasing. We could say that it's increasing since it's flat, but all of the other reference functions in this table are all strictly increasing. remember the logarithmic function is very slowly increasing. Remember that when you double the value of n, you increase the value of the logarithm base 2 of n only by 1. Remember that when we don't indicate the base of the logarithm, we always mean base 2. But actually, the interesting thing is that in a big O notation, the base of the logarithm does not matter. So log base 2, log base 3, or whatever base you're interested in, we're always going to write the big O relationship as big O of log n. Now, if you want to understand why, go back to the definition of the logarithm. And you'll realize that when you go from one base to another, all you're doing is multiplying by a constant. And that constant, again, gets wrapped up in the witness, the constant value c that is defined or part of the definition of the big O relationship. So even if you change the base of the logarithm, you're just multiplying this function by a constant, and the big O relationship does not change. So this was the logarithmic function. The next observation I want to make is about this class of functions. Notice so far, when we talked about polynomial functions, all the powers of n were integers, 1, 2, 3, and so forth. Now this function is different. It's not a polynomial function because the power of n is a real number between 0 and 1. Notice if k was equal to 0, n power 0 is 1, so it would reduce to the constant function. And if k is equal to 1, then n power 1 is the linear function. So this is the intermediate case between the constant function and the linear function. So k could be, for example, the real number 0.1 or the rational number 1 over 3 or 1/3. The interesting case is when k is equal to 1/2, you should remember that n to the power 1/2 is the same as the square root function. So check it out. If you take the square of this function, you get square root of n squared is equal to n by definition of the square root. Now if you square this number, you're taking n to the power 1/2, and you take all of that to the power 2. In other words, you're taking n to the power 1/2 times 2, which is 1. So you get n again. So the interesting thing to realize is the square root function is also a reference function, namely n to the power 1/2. And in particular, what this table indicates is that the square root function grows faster than the logarithmic function. In fact, any function of the form n to the power k, when k is strictly greater than 0, all of these functions grow faster than the logarithmic function. So to make this very clear, just realize that for this particular row, let's focus on that one, which is kind of the new one here, k can be as close as you want to 0 without being equal to 0. So k could be 0.0001. Realize when you raise n to that value, that function grows very, very slowly. It doesn't matter though. The point is that whatever positive value of k you take, n to the power k, as slowly as it grows, still grows faster than the logarithmic function. That's what this table indicates. In particular, just remember that the square root function grows faster than the logarithmic function for that reason. Now let me conclude the discussion of this table by reminding you why the function n log n grows faster than n, but not as fast as n squared. The easiest way to remember this is to consider n as being equal to n times 1, and this function being equal to n times n. So if this is n times 1, n times log n, n times n, the first n is common to all three functions. So the only difference is the second term in the multiplication, and we have 1 here, log n here, and n here. So since log n grows faster than 1, the constant function, and log n grows slower than n, as we argued before, then n times 1 doesn't go as fast as n times log n, and n times log n doesn't go as fast as n times n or n squared. So the rest of the table should be familiar to you already. So let me conclude this segment by asking you the following question. Let's say I ask you to prove that the function f of n equals log base 2 of n is big O of square root of n. Well, in general, this kind of result is pretty hard to prove because you have to prove a relationship between the log and the square root function. But the point I'm trying to make here is you don't really have to prove anything here. You just can refer to this table to answer this question. And the answer to this question is yes, log n is big O of the square root of n because log n appears higher in the table than the square root of n function. So the message here is that from now on I will assume that you know this table and the order of the rows in this table by heart, and the rest of the lecture, or at least the next couple of segments, will be examples of how to use this table to prove big O relationships of arbitrary functions.